Hello and welcome back to BioRules video lessons. Today we are going to be talking about methods to sample the size of populations. So how do we estimate population size? Okay, if you have a motile organisms that move around, they might not be very easy to count. And they may be counted twice because they may move. You count it there and then they move to the side, you count it again. So can you imagine yourself counting butterflies in a place like this? It's probably going to be an impossible mission. So for this kind of estimate, when you have motile, difficult to count organisms, we have a technique called CMLR for capture, mark, liberate, and recapture. So it's also known as the capture-recapture method. Okay? How does it work? I'm going to be building here a population. This will take a while. I'm going to be speeding up this quite soon. But we're going to have a population here, and we're going to be marking some of these butterflies in a first capture. We're going to spend some time capturing some of these butterflies, and we're going to be marking them. So once we do that, then we are going to be carrying on. So I have here an entire population. Let's say I put some effort and I manage to get those numbers of butterflies. So I capture them. This here I'm going to be capturing and marking. And I'll call this my N1, my first number and my estimate. N1 in this case was 15. Now I have 15 butterflies that have been captured and have a little red dot in the wings. So later what I'm going to be doing, I'll let them go. Actually, in butterflies, we capture, mark, let them go, capture, mark, let them go, and they are going to be mixing around in the population. So after a certain amount of time, these butterflies are going to be mixed around. And then what do? I capture a certain number of them again. In this case here, I'm putting an equal effort to capture the same number. My N2 here, my capture in the second time is going to be 15 as well. So I caught 15 butterflies at random in the way that they appeared, that they showed up. So what do we do here then? I'm going to be seeing how many are marked. So I count there 1, 2, 3, 4, 5 of these are marked. So if I mark the first time 15, and then I capture 15 randomly mixed in the population, and 5 of those are marked, how big is this population? Give me a number. Think. What would be the number? And when you're going to be talking, I'm going to be asking you, what was the number that you guessed? Okay? But what we're going to be seeing here, actually, instead of guessing the number, and actually there are some of you that probably got the correct number because I made some easy numbers over here, but there is a method that you can use those values to actually estimate the population size. So in this case here, the population estimate is going to be the N1 times N2 divided by N3. So the number that were captured and marked in the first time, multiplied by how many have been captured in the second time, no matter if it had marks or not, divided by how many of those are marked. So in this case here is going to be 15 times 15 divided by 5. So 15 times 15 divided by 5 equals 225 divided by 5, which equals 45. So the estimated population in this method here is 45 individuals. Okay? This method is quite efficient as soon as we have some situations that we take care of. Okay? Just to illustrate, this is a real butterfly. It's called the Liconius natereri that I marked and photographed in my research in Espírito Santo. This was the P02, okay, and you can not only put a little dot, you can even write numbers in there, so you can actually identify butterflies individually. Okay, so capture-recapture method is also known as the Lincoln method, and what should we think? They are usable for motile organisms. Why? Because the organisms, they must mix between the captured. If you mark plants and then you go back and they didn't mix around, so the method is going to be biased, is not going to be a good estimate of how many are in there. Okay? It is expected the population to be closed, or at least fairly closed. What does that mean? Nobody's getting born, nobody's dying. So depending on the method that you're going to be using, it is quite interesting for you to leave enough time between samples for the population to mix, but not too long, so some are going to be born or some are going to be dying. Because if some are born or some are dying, they are going to be changing the numbers that are in the population, so they may change your estimates and they reduce the accuracy of your estimate. Okay, so natality and mortality should be equal or very close to 0. Okay, the mark must stay. Of course, if you mark an animal, the mark goes away, and then you capture it again. If you assume that that animal wasn't captured before, then you are going to be having a problem in your population. You are actually going to be overestimating your population because you're going to be dividing by a smaller number. Not good. You also shouldn't have trap scary animals, or at least not much trap scary. What trap scary means? If an animal got too scared when it was captured the first time, it may avoid that method of being captured the second time. This is actually famous for some species of butterflies. They see that gigantic guy running with a gigantic coffee filter and catch them in the first time in the forest. The next time they see that giant with the gigantic coffee filter again, they are going to be running more. Some butterflies, they are trap scary. So in that case, we have to take that into account, thinking that we might be overestimate the population size because some that were marked, they are less likely to be captured again. Similarly, we should have no trap happy. Some animals like when they have been trapped. For example, if you use food to attract animals to a certain cage and the animals don't suffer when you capture them, they may see that same cage next day and say, hey, woo, free food. I will spend some time locked in there, but I will eat for free and then I will go away. So if you have trap-happy organisms, then you might be underestimating your population. So all this should be taken into account. Preferably, you shouldn't have an open population. The population should be closed, the market should stay, and no trap-happy, no trap-scary individuals. Okay? Very good. So what do we do if we want to estimate the population size of sessile organisms? In that case, no, we cannot use capture-recapture because they are not going to be mixing. But on the other hand, they are easier to count. They are not moving around. However, they might be way too many. So in situations that there are too many, you're not going to be capable of counting every single one of them. Okay? If you have a very big area that you cannot cover at all, you're also not going to be able to count every single one of them. So in that case, you use another method which is called the Quadrat method, which the name already gives the spoiler. You make a quadrat, you make a square. And in that quadrat, which can be terrestrial or aquatic like this here, you go there and you count how many individuals are in a certain square. Okay? This one here is a quadrat to count small stuff, so you have very small quadrats, but you also can have very big quadrats. There in Honduras or in Dominica, we estimated trees and plants population in a 10 by 10 square. Actually, in Dominica was a 10 by 10 square. In Honduras was a 20 by 20 meters square. So it can be big, can be small. It depends on what you're going to be sampling, okay? So basically, you use quadrats. But when you use quadrats, you're not counting the population. You are actually estimating the density of individuals in a certain area. So be aware of that. Quadrats estimate density. Okay, I'll give you an example here of a quadrat method. Let's say that I want to count the organism in a known area. I should know the estimate, but actually I'm going to be calculating all the organisms that are in a tiny little known area. Then I estimate the density. For example, let's say that I threw a little square, 10 by 10 centimeters, into a grass patch. And I count how many grass blades are there. In this example here, I counted, let me say, how many leaves are there? 14. 14 leaves in a 10 by 10 centimeter square. So if I do the calculation, I have 14 leaves in 100 square centimeters. That means that I have 0.14 leaves for every square centimeter, or I have 1,400 leaves for every square meter. So either of them are going to be working, okay? You can have whatever unit you want, but once I know the density, now I know how dense that population is in there. And actually, this can be quite helpful because if I estimate the density, I might be able to estimate the population. Okay, again, it's an estimate, I'm not going to be counting them all, but I can use the density to estimate the population. How do I do that? Quite simple. If you know the density and you know the total area, it's just a matter of doing a ratio proportion. So, for that example, let me say we went to a football field and we count how many grass blades are there in a 10 by 10 centimeters. So, how to find the population knowing the entire living area. So, football field, 100 meters by 75 meters sides. So in that case over there, I will calculate the total area. The total area here in square meters is 7,500 square meters. So now it's quite easy. No, I can do the ratio and proportion. If I have a density of 1,400 blades per square meter, that was my estimate in the previous calculation. Now, how many individuals, my population, I will have in 7,500 square meters? Very simple. Then the population here will be 1,500 times 7,500 square meters divided for 1 square meter. If I cancel that, I'll find my sample that is that, about 10,500,000 grass blades in a football field. This is an estimate of the population size based on the density. Okay, so Quadrat limitations. Okay, organisms must not move, or at least must not move much, because if you throw a little quadrat in those butterflies that I showed in the beginning, they are going to be running away. They'll fly away actually, and they're never going to be able to count any. So they should be quite not movable. Okay. Organisms must be uniformly distributed, especially if you want to use the density to estimate the population. However, uniformly distribution is almost impossible to have in natural populations. So in that case, if they are not evenly distributed, so if they are like that, then there is a solution. Okay? You must make repeated samples. You sample once over here, and then you sample over here, and then you sample over there. But very important when you repeat samples is that the samples, they must be random. You must randomize where you are going to be putting your quadrats so you can make the estimates. Okay? I hope you had fun watching this. We are going to have practicals about that later, but now you have a questionnaire to answer and see if you got the idea. I see you in another class.